This is the course presentation on application of selected linear algebra processing methods in the electromagnetic flow measurement for open channels, presented by Sudhir Singh Yadav and Varsha. This is the abstract of our presentation. The paper taken for the course project presents a quantitative comparison of a trial that modifies the inner product in such a way that it would be blind to the existing disturbances with the approach based on the extension of the non-orthogonal basis. Starting from the introduction, electromagnetic flow meters measure the average velocity even when the filling of the channel varies and local stream fluctuates. It works on Faraday's effect. According to the Faraday's effect, two different types of voltages can be simultaneously generated in any conductive liquid that moves relative to the time-variant magnetic field lines. A schematic diagram of electromagnetic flow meter is shown in the slide. For open channel flow measurement, two parameters are considered, that is velocity of medium and filling of open channel. Velocity of medium is denoted by small subscript v and filling of channel is denoted by small subscript h. Now, the signal generated by Faraday's effect is represented by ut. I1t describes current waveform responsible for existing magnetic fields and I2t is its first order differentiation. Now, signal processing methods are employed to determine the amplitudes of W1 and W2. Main problem in determining these amplitudes is the uncertainties caused by the low frequency components in flow measurements. Now we will discuss classical least square approach in brief. Current signal is obtained by data acquisition and numerical differentiation. To remove the noise from the signal, discrete wavelet transform is used to decompose the signal and the inverse transform is performed. Only after that numerical differentiation is done. Now we can write our combined signal in matrix form as depicted in the slide, and thus we can find amplitude of W by least square approach. But this least square estimation is very sensitive to low frequency disturbances. As we can see in the slide, least square estimators are linearly dependent on real flow parameters, but have high variances that must be reduced. For that, we can use polynomial approximation method. In this equation, dt represents some disturbance that is modeled with polynomial approximation. But fundamental problem with this is the system brings the need to calculate and invert the matrix. As the inversion may be inaccurate or close to singularity, we resort to some linear algebra processing methods that will reduce the variances and problem of matrix inversion completely. Linear algebra approach is discussed from here. I1t and I2t now be treated as vectors, and ut will be an element of two-dimensional linear space spanned by these two vectors. W1 and W2 are now scalars that represent signal ut in finite two-dimensional inner product space. Standard procedure is based on Gram-Schmidt process that result in the formulation of orthogonal bases and orthonormal bases. We decompose our acquired signal as shown in the equation and can recover the original flow parameters W1 and W2 by just equating the orthonormal and non-orthogonal bases as depicted in this slide. Some disturbances are added to the acquired signal and the new vector is an of infinite dimension. According to the orthogonal projection theorem, when there is a finite orthonormal n-dimensional basis of vectors, then there is also a unique linear combination of them that approximate to the way shown in the slide. Any disturbance orthogonal to the elements of the basis does not affect the value of WWK that is governed by the linearity property of inner product. So, so now we can remove any disturbance that is orthogonal to our basis vectors. From the figure, we can see that in figure 6, two vectors are shown that are orthogonal to each other. But in figure 7, vectors shown are not orthogonal. Thus, we will define a weight vector v that will make the two vectors orthogonal to each other. Thus, our main goal is to find vector v such that disturbances are much more orthogonal to basis vectors. That is, inner product of D and orthonormal basis I is minimum. Weight vector must be non-negative, and in finding minimum of product vectors, neglect vectors containing too many zeros, as this will cause information loss. This figure shows the difference between the Euclidean and proposed inner product, and we can see the difference very clearly that proposed inner product has very low variances in the amplitude levels as compared to the Euclidean product. Now we proceed to our conclusion of the topic. High standard deviations in flow measurements significantly reduced. Proposed signal processing method gives lower standard deviations compared to least square approach. Thus, power consumption is reduced and SNR is highly improved. Use of orthonormal basis avoids any matrix inversion and number of multiplications reduced to 4n, where n is the number of equations. Uncertainty in flow measurements are now can be reduced by use of proper inner products. This is the end of our presentation. Thank you.